Okay, so today, myself, Daniel, Blake, and Kassar will be presenting a paper by the name of Fast is Better Than Free, Revisiting Adversarial Training. The authors of this paper are Eric Wong, Leslie Rice, and Zico Coulter, and this paper was presented in the International Conference on Learning Representations in 2020. It has roughly 130 citations, and we've also included both the paper link and also the code link for the work below. Just to outline the presentation for today, we're going to start off with an abstract of the work and then dive into the introduction of the technical contributions. Before diving too deep, we'll cover a bit of background and related work. Specifically, we'll explain both the fast gradient sign and projected gradient descent adversarial attacks, and then discuss a little bit how these are used for adversarial training. Then we'll dive into the technical contributions of this work, which is a fast adversarial training method with FGSM. Specifically, we'll provide an algorithmic comparison to previous state-of-the-art, and then discuss some of their experiments, results, and comparison to PGD-based training. To finish up, we'll provide a conclusion of the work as well as arguments both for and against the paper. The motivation for this work is that adversarial training typically comes with a very large time and computational overhead. This is due to the strongest attacks requiring multiple forward passes and gradient computations. For example, two typical, popular, and strong attacks that we've covered in the class are PGD and Deep Fool, both of which require multiple forward passes and gradient computations to generate an adversarial example. This time and computational overhead has slowed progress in neural network robustness search. So to combat this, the authors of this work asked the question, can we leverage one-step methods, such as FGSM, to the same effectiveness as multi-step methods, such as PGD, for adversarial training? To introduce the technical contribution of this work, we briefly describe this FGSM adversarial training method. The main finding that the authors find is that FGSM adversarial training, specifically combined with random initialization, can be just as effective as PGD-based training. FGSM adversarial training is significantly more efficient than multi-step methods, and authors find that training time can be nearly equal to standard training. These findings are quite significant because FGSM adversarial training was previously thought to be ineffective. Authors also adopt general training strategies to further improve their adversarial training time. Specifically, they leverage a cyclical learning rate and also mixed precision training. The combination of their FGSM-based adversarial training method combined with these general training techniques produces robust networks in state-of-the-art time. Specifically, authors are able to produce 45% adversarial accuracy on CFAR 10 in just 6 training minutes compared to the previous state-of-the-art of 10 hours. Similarly, authors are able to achieve a 43% adversarial accuracy on Imagenet in just 12 hours compared to the previous best of 50 hours. To start off, we'll provide a brief description of the fast gradient sign method. This is an adversarial attack algorithm that requires a single gradient computation. Its procedure is visualized below, where we start off with an input example X and its ground truth labels Y. The loss between the example's prediction and the ground truth are computed, and then we compute the gradient of the loss with respect to the input itself. We then take a step in the direction of the gradient with a magnitude of epsilon. This single gradient step computes the adversarial perturbation generated from fast gradient sign. This is a white box attack, meaning we do require the model weights, and it's also an untargeted attack. Our FGSM is a variation of FGSM which randomly initializes the perturbation, rather than starting from a zero initialized perturbation. Tramer, the authors of this original work, initialized with a non-uniform noise, and this will be important going on later in our presentation. It should be noted that early attempts at FGSM-based adversarial training did not succeed, although the authors of this work argue that this is due to specific implementations of the initialization or a complete lack of random initialization. I briefly describe what it's like to randomly initialize the perturbation. It's essentially equivalent to adding some noise matrix to the perturbation. So rather than starting from a zero initialized perturbation and then we just add the magnitude of the gradient, we start off from some random initialized noise and then add on the sign of the gradient. Projected gradient descent, or PGD, extends previous one-step methods with a more powerful multi-step gradient-based attack. This is essentially equivalent to an iterative FGSM attack. Again, this is a white box attack, although PGD is now capable of both targeted and untargeted attacks. PGD increases the time complexity of generating adversarial examples by a factor of n due to requiring multiple iterations of gradient steps. It should be noted, however, that multiple gradient steps tends to produce significantly stronger perturbations than a one-step method like FGSM. As such, this powerful adversarial attack has seen great success for adversarial training. However, the obvious downside is the runtime and compute costs of the inner loop during adversarial training. So specifically, this work looks at how we can alleviate the need for this inner loop during adversarial training.
So now that we've covered a couple techniques for calculating perturbations, let's actually apply those perturbations. So in adversarial training, hold on. Okay, adversarial training simply involves training a network on adversarially perturbed images. So some perturbations, delta, is calculated in real time for the network, and those perturbations are applied to the training data images to create the adversarial examples. And the losses created from those adversarial examples are used to make the network more robust and or more robust to other adversarial examples that that it would not have been otherwise able to train against. And calculating, and so since training is a costly task, it's also important to reduce make calculating perturbations efficient as well. And so for adversarial training, there are a couple methods that we'll be covering here that we just went over a second ago. PGD and fast gradient sign method. And PGD is one of the most common methods for adversarial training, and was one of the best. And fast gradient sign method, for the fast gradient sign method, prior work indicated it was not as effective, interestingly enough, until a new type of adversarial training came out called free adversarial training. And we can see here below that an example equation for adversarial training. You can see we take input x and apply a perturbation delta and then pass it into the model, which gets an output, which is then compared against the ground truth, and then the loss is calculated, related to those two. And finally, that is used to then update the model itself and make the model more robust. Now, one of the original standard forms of adversarial training was with PGD. And PGD, so it was used to calculate the perturbations delta. But the problem with that was the gradient computation is performed or proportional to OMN each epoch. So it's very expensive, very costly to perform. And so, like, as a comparison, standard gradient computations are proportional to OM each epoch, where M, by the way, is the size of the data set, and N is the number of steps. And so, thus, PGD adversarial training is much more expensive than standard training. One is an OM complexity, another one is an OMN complexity. Now, free adversarial training makes some improvements. It's FGSM-based perturbation. It uses FGSM-based perturbation calculations, and amazingly, the gradient computations are proportional to OM each epoch, which is, like I said before, it's comparable to standard training. It's great. It's much more efficient. And they're able to do this with something called mini batch replays. Model weights are updated alongside the FGSM attack, resulting in less computation. Now, there are some parameters that have to be set that make this a little bit different. Step sizes are set to equal epsilon, and in order to remove the complexity of n, because we still, so in free adversarial training, steps are still taken, but to prove that that it's actually OM complexity, we can divide the number of epochs t by the number of steps n, and then only compute a number of epochs where t is divided by n, and then that removes the complexity of n from our and leaves us with an OM complexity. You'll see what I mean soon when we get to actually looking at the algorithms themselves. Now, fast adversarial training is what's detailed, what was invented in this paper, and fast adversarial training is also FGSM based, and but what makes it a little bit different is that it incorporates the random initialization of perturbations. Now, this was previously seen in Tramer et al. However, it wasn't applied in quite this way. And this paper also makes an improvement on Tramer et al.'s use case. And that improvement is a uniform random distribution for the random initialization of perturbations. A uniform random distribution is proven more effective than the random initialization that Tramer et al. Had, which was I'll show you later on in the algorithm for that training. And empirical evidence presented in this paper indicates FAST has a comparable performance to that of PGD. So that's very important. This adversarial training method is fast, and it's effective, and it's accurate. And so when researching fast adversarial training and FGSM-based perturbation calculations, the authors of this paper made a note, and they found that if the step size is equal to epsilon and zero initialization is used, it's too weak, and the result is not guaranteed to lie on the LNF ball boundary, which of course is very bad. And the FGSM steps, and when the FGSM step size is equal to 2 times epsilon, this leads to catastrophic overfitting. Catastrophic overfitting is a concept that is covered in this paper, that's introduced in this paper. And essentially what you need to know is it's bad. It causes training to fail. But with if you set the step size equal to 1.25 times epsilon instead, the model robustness is significantly improved. It's much better than setting the step size equal to epsilon or the step size equal to 2 times epsilon. Also another thing to note is just as free adversarial training was OM, fast adversarial training is also performs OM gradient computations, and this is thanks to many batch replays mostly, and the removal of step sizes. Sorry, of number of steps. Now let's compare the algorithms themselves. So first we went over standard PGD adversarial training, and so this is the algorithm for PGD adversarial training. We can see here this T represents the number of epochs. So this loop is for the epochs, and then M represents the size of the data set. And then as we get in here, we get into the meat of the attack. We can see how PGD is performed here. This loop here with N is the number of step size is the number of steps to perform for this training algorithm, and you can see how it loops over N times, and it continuously performs these operations. It's a lot of operations, very inefficient. And then at the end, the model weights are updated. Now, if you look at the free adversarial training algorithm, we can see the epochs are actually divided by N instead. Even though there's an N loop inside, we can divide the number of epochs by N in order to basically negate that complexity. And so it's not really OM N for each epoch, it's really just OM. And we can see here that the mini batch these are the mini batch replays, and that you can see the model weights are being updated alongside the attack. Right here, I'm just pointing out T divided by N, and then the inner loop canceled out by T divided by N. And then finally, we have our fast adversarial training algorithm. And in here, we can see we have no N loop at all. And actually, T is not divided by N here. It's just T. So we're able to leave it as just T because we get rid of N entirely. And instead, we randomly initialize the perturbations here in a uniform distribution, just like we said before. And then the attack is performed, and the model weights are updated all in one swoop, all at one time. Now fast adversarial, some improvements were made to their fast adversarial training algorithm. That algorithm before was just a basic overview, general understanding of fast adversarial training. There is a benchmark. There's a benchmark called DonBench, and people compete to train networks as quickly as possible. And so this paper incorporates those techniques into their work to reduce the training time. And so some of those techniques used in DonBench that were incorporated are cyclic learning rate. And cyclic learning rate is just scheduling a learning rate to change linearly between 0 and some max rate. We'll have some graphs for that in a second. And mixed precision arithmetic is another technique that was used, and it leverages GPU Tensor Core's half precision computation capability. And this also reduces memory utilization and runtime. And then here we can see our graph. So here's an example of cyclic learning rate graph. Here we can see our learning rate on the y-axis, and these are the epochs on the x-axis. You can see as we iterate, then the learning rate changes, and this actually results in a much quicker training time on data sets such as a CIFAR 10. And here we have the same thing for Imagenet, learning rate going up, going down, and then across.
So now we look at different experiments that they conducted using MNIST, CIFAR10, and Imagenet datasets. For CIFAR10, they use a ResNet 18 model, and for Imagenet, they use a ResNet 50 model. They perform FGSM training using random initialization techniques, downbench techniques such as cyclic learning rate, mixed precision using the NVIDIA's Apex package. And for Imagenet, they use O1, Apex mixed precision training, and for CIFAR10, they use O2. And like Blake mentioned, they use a standard step size of 1.25 into epsilon. And these models that are trained are tested against PGD techniques with 10 random restarts and a total of 50 iterations with a step size of 2 by 225. For the MNIST results, they compare, they use two small convolution networks with 16 and 32 kernels each and having a 100 unit fully connected layer. We can see here that the PGD and the FGSM perform fairly similar in terms of standard accuracy, and they even compared this with other adversarial attacks like PGD with epsilon 0.1 and 0.3. Now, verified is another PGD attack which just uses mixed precision training, linear programming. So the only difference that we see in all of these results that are fairly similar is for PGD epsilon 0.3, which where FGSM performs better PGD performs better than the FGSM model. For CIFAR10 results, they compare, again, various adversarial networks using downbench techniques. So here we see FGSM with different downbench techniques and zero and random initializations compared against standard models, the standard accuracy, and compared against the PGD attack and the time taken for the model. And here we can see that the FGSM model with random initialization performs the best in relatively low time. They compare these results with free adversarial training. And here, although free adversarial training gives out similar robustness of the model, it takes significantly longer. They also do the same with PGD trained model, and the PGD model performs the best, is the most robust compared to all of them, but it again takes significantly longer to train. Now they compare the amount of epochs required to take to reach the minimum 45% robust accuracy. And here we see a graph of these blue and orange dots, where blue represents the adversarial examples and the orange dots represent accuracy against natural images. And these data points are the average performance over 3 independent runs. And for FGSM, it takes around 15 epochs to reach a robust accuracy of 45%. For PGD, the number of epochs is way lower, is around 10, but we need to note that the iterations inside each epoch is significantly higher, so this would take longer. For free FGSM, the number of epochs required to converge is required to reach 45% accuracy is 80. They show the same results over here with the exact amount of time taken for each of these methods. And we can see that the FGSM with downbench techniques performs the best with 6.34 minutes to reach 15 epochs. So now for Imagenet results, they compare different FGSM models amongst each other to find out the best model. They do so by using single precision, and they compare FGSM with free training. Here we can see that FGSM gets to similar accuracy in a significantly lower time. They do so again with mixed precision training, and again we see the same results. And they carry forward this method, which is in 12.14 hours for the other comparisons. So now they compare the FGSM, this model, with the free training with an epsilon of 2/225 against standard accuracy and then different PGD attacks. So here we can see that against different attacks, they performed fairly similarly, but it is interesting to note that the free training performs better in terms of standard accuracy. So we see the same, again, the similar trends with epsilon of 4/225. And here, this is the most robust in significantly low time. The authors mention a few bad techniques that were previously used, which led to the failure of FGSM adversarial training. And some of those causes would be zero initialization in the beginning, taking a very large of a step size, scheduling the learning rate at bad points, and then the number of epochs itself. Now, the number of epochs, it is interesting to see because the authors also plot this, and they say the solution for this would be to early stop the model before. Here we can see the graph itself, which shows loss versus epoch for FGSM training, which is shown in orange, and then the PGD testing. We can see after a point, even though the training loss reduces significantly, the test loss goes very high. Similarly, we can see the trends again with the same models in terms of percentage error. And we can notice that it is somewhere around right before the 15th epoch that they mentioned previously in the results that is ideal for early stopping in order to not overfit the model.
So in conclusion, FGSM, specifically with a random initialization, provides an efficient yet powerful approach to adversarial training. Some key takeaways that the authors described from these experiments. One is that adversarial examples during training need to span the entire threat model, and that lack of random initialization may have caused FGSM's weak performance thus far. So by spanning the entire threat models, what the authors mean is that previous initialization strategies, either a complete lack of random initialization or also Tramer's non-uniform initialization approach, don't essentially span the entire threat model in the way that each pixel in the perturbation, they find that each pixel in the perturbation is either set to 0 or plus or minus epsilon value itself. And there's no sort of perturbations in the middle of that range. And so during training, our model is not necessarily seeing all of the sort of possible combinations of perturbations. And so random initialization, as performed in this work, allows our adversarial examples to essentially span the entire threat model, or each pixel is always perturbed at least slightly during training. and this produces more robust models, as these experiments show. Another key takeaway from these results is that defenders don't need strong adversaries during training. And by strong adversaries, we mean strong adversaries are typically referred to those from PGD. And so previous work hypothesized that only strong adversaries would result in strong adversarial training. However, this work shows that rough approximations via FGSM are sufficient for robust models. Lastly, the authors show that standard training improvement strategies still work for adversarial training. So this is just referring to the cyclic learning rate and mixed precision. And they're just showing that these strategies can be used not only for standard training, but also for adversarial training. So a very strong argument for this work is that FGSM fast adversarial training allows adversarial training to be just as fast as standard training, where previous approaches were much, much slower than standard training. Another strength of this work is that the random initialization step is very simple to implement and to leverage. Moreover, the work shows extensive experimentation and comparison to other approaches, which I thought was very key for this paper to be strong, being that most of their contributions are purely empirical. I thought it was a very good thing that they provided such extensive experimentation in order to further back their hypothesis. And again, they show that their results are extremely strong in that this fast adversarial training method can produce robust models just as strong as PGD. And again, this is a vast improvement over previous baselines. Lastly, the authors take the time to both discover and analyze these catastrophic overfitting scenarios, and they also provide several different tips or advices for how to prevent this scenario. So in terms of arguments against this paper, I think one clear thing is that this work is not incredibly novel. And the contribution and results are purely empirical. So one, FGSM adversarial training has been studied before. And not only that, FGSM specifically with random initialization has also been studied. It is true that this paper presents a slightly novel approach to random initialization, but the idea itself has been looked at many times in the past. So here again, this is the paper that introduces random initialization. Moreover, the authors spend a lot of time talking about cyclic learning rate and mixed precision, but this has already been shown extensively in previous work as well. So both in my own sort of personal research and also looking at reviews for this paper, I found a couple other works that use both random initialized FGSM and also standard FGSM for adversarial training. So this just shows how the ideas and approaches that this paper used have been looked at before. So here are a couple different papers that use either RFGSM or standard FGSM for adversarial training. It should be noted though that this work does result in the strongest performance. And so although the contribution is somewhat small, I think it is also important to note that this significantly outperforms previous approaches. Lastly, I would be interested to see how this compares against more recent attacks. The authors tend to focus really only on FGSM and PGD. However, there have been a lot of really interesting developments in terms of both adversarial attack and defense. So I would have liked to see a bit more comparison against recent attacks as well. Thank you.